So there's one more type of linear transformation I want to talk about, and that's projections. One other way of doing this, one other way of thinking about this is a full squash. So unlike many of the previous linear transformations we talked about, this one's actually going to lose some of the dimensions after you apply the transformation. So what we're going to do is we're going to project onto a line, and that line will be ABT. So that just means we pick some vector AB, and we just stretch that back and forth for as far as we can, and that defines a line. And we want to figure out that what happens when you take and squash. By projection, we mean we're going to squash on this line perpendicularly. So it's not just like it's not zeroing out the X or Y coordinate. It is actually, you have to figure out what the angle of that line is and actually squash it down. And so this is going to give us a picture where, unlike before, all the vectors are going to lie on a line. If you take the other standard vector, right, that one's also in this case going to lie on a line. And if you take some other vector, this projection is then just going to get squashed down to this line here. So everything's getting squashed down to a line, and so the after picture is just a line. So it loses one or more of the dimensions that it had before. The formula for this is a little complicated. It involves dot products. You're probably using dot products without realizing it. So just a reminder is that a dot product between u and v, for example, if you have two vectors that look like this, the dot product just means we're going to multiply the like components together and then add them up. So one way of thinking about the dot product is there's some measure of similarity. In fact, geometrically, the dot product is also equal to the lengths of the vectors times cosine of the angle between them. So if you have two vectors that are in the same direction, they're going to be positive. And if you have two directions in kind of opposite directions, it's going to be negative. And moreover, if you have things that are exactly perpendicular, you're going to get 0. And so the dot products let us use a projection formula. So the projection of u onto v is just equal to u dot v over v dot itself times v. So keep in mind, this is just some scalar right here. This is a scalar quantity. And this just tells us how much of v is in the projection. So when we define our line AB, right, we define our vector AB and we define the line that goes on it. When you project onto it, when you squash onto it, every vector is going to end up being some multiple of AB. So the projection just says, how much of that vector do we have? And this is given by this formula. And so if you go through the steps and figure out, okay, where does 1, 0 go to? It turns out it goes to a squared over a squared plus b squared, and a over b, a squared plus b squared. And likewise, 1, 0 is going to go to ab over a squared plus b squared, and b squared over a squared plus b squared. So altogether, what matrix do we end up with? Well, we end up with a matrix that looks like this, but I'm going to simplify it lightly. And notice everything has an a squared plus b squared in the denominator. So we're going to kind of put that on the side. And so you end up with something that looks like this. And we can take the matrix to look like this. So the matrix is kind of nice. It looks kind of fugly because there's a lot going on. But this is a matrix that corresponds to just squashing things down. If you pick a squared plus b squared to be 1, then this is a really nice matrix. So if you pick it to be what's often called a unit vector, it's a really nice matrix. It's just a squared, ab, b squared. And we're going to study a lot about different types of transformations, different types of matrices that give you a squash. So this is one thing just to keep in the back of your mind, that it's a linear transformation can do a squash, but it's not always going to happen. It sometimes happens, and we want to figure out what properties that means. What do we lose when we do that? And we're going to study more about that going forward. Just keep that in the back of your mind. Yeah. One other thing I want to mention about linear transformations are inverses. So now that we've defined linear transformations geometrically, we can talk about what undoes them. So for example, we might define a rotation of pi over 3 counterclockwise. And from before, we know that the matrix is then going to be just a cosine sine matrix. Okay, I wrote that in way too many different ways. So there we go. Right, so that's the matrix. This is the matrix. This corresponds to this thing. Right? But now what undoes this? So we want to ask the question, if you rotate pi over 3, right, and you end up with this vector, what transformation is always going to get you back to where you started? Right. Well, intuitively, if you rotate plus pi over 3, the inverse is going to be a rotation of pi over 3 in the opposite direction, or since we should generally measure angles counterclockwise from the x-axis, it's an angle of minus pi over 3. So we just end up with a different matrix. And this matrix is called the inverse because it undoes the first one. It corresponds to a transformation that undoes the first one. And this is just the rotation to get you back to where you started. One thing that's a little bit weird about transformations is that when you want to inverse them, you have to do the reverse order. So this was kind of a simple example where you have one simple transformation that's easily described. But now, what if we do instead, we want to do transformation. Suppose your transformation is reflect about the x-axis. Then stretch by 2 in the x direction. So that's a very simple transformation. What does this transformation do? T does this. T is going to reflect about the x-axis. So the very first thing that's going to happen is, keep in mind the x-axis is this line. So the first standard vector doesn't do anything. And then we're going to stretch by 2 in the x direction. So we're going to stretch that vector by 2. But the second standard vector does do something. It's going to reflect about this thing. So it's going to reflect downwards, but it's not stretched. So you end up with this picture. So if you started with this unit circle right here, you would end up with kind of an ellipse. And now what we want to do is we want to ask the question, if we undo this process, how do we do it? Well, to undo it, we have to do things in reverse. So the one key point I want to emphasize is that undoing has to be done in reverse. So in this case, T inverse, the inverse transformation, what has to be done first? We first have to undo the stretch by 2 in the x direction. So we're going to contract, that's going to be a 1/2. We're going to contract by 1/2. That's a times in the x direction. Then, right, we did this one first. And now we go to the last one, which is in this case, reflect about the y-axis. So what undoes reflecting about the y-axis? Well, if you want to undo reflecting, you just reflect back. So reflecting is something that it's its own inverse. So we're going to reflect back. So what does this look like? So if we do this, we're going to contract by a factor of 1/2 in the x direction. So we're going to shorten that vector by a factor of 1/2, and then we're going to reflect about the line, sorry, about the y-axis, it's the x-axis. This should be an x-axis. My apologies. So we're going to reflect about the x-axis. So in this case, that's not going to happen. So we have that if you do the transformation, if you undo them backwards, you start at 1, 0, and you're going to go to 1/2, 0. And likewise, if you take 0, 1, you contract by a factor of 1/2. There's no x's here, so it's just itself. And then you reflect about the y-axis, and you end up with 0, 1. Okay, so what does this say? This first transformation, what ended up happening? So T can be described by the matrix. We got 2, 0, and 0, minus 1, 0, and minus 1. But for T inverse, what ended up happening? T inverse we can describe by 1, 0 went to 1/2, 0, and 0, 1 went to 0, minus 1. Right, so I should mention in this case, it seems kind of cool, but it's a coincidence that in fact these are kind of the inverses of each other. But on the other hand, you'll notice that up here, when we did the rotation, that's not going to be true. You can't just take 1 over each of the entries to get over here. So the inverse transformation is not easily described as a matrix. You kind of have to step through it. But the key thing is that it turns out that we're going to learn next time that these are in fact inverse matrices. These matrices are inverses of each other, and these matrices are inverses of each other. And the key thing is every transformation, every linear transformation that is encoded by a matrix, there's going to be some other linear transformation, most of the time, that undoes it. To see a linear transformation that's not undone, so this is a warning, not every linear has an inverse. Right? And so just geometrically, what's one where that doesn't work? That's the projection. So for example, if I have two vectors, I might have two vectors. I might take this vector, which comes right down onto it. And then I might take a different vector that comes down right on the same thing. So now, since everything lives on the same line, I can't undo it. I don't know when I'm at that exact spot. If I end up with this vector, I don't know if I started with the red, if I started with the green one, or I started with the blue one. Which one did I start with? So this means we can't undo this. So this is not invertible. Right, so not every matrix is going to be invertible. Not every transformation is going to have inverse. For another example of one that's not invertible, this is an extreme example, is if we take every single vector just goes to the zero vector. So in the same way, every vector goes to the zero vector. So this is the transformation. This is just the 0, 0 matrix. This is the totally zero matrix. That's a linear transformation because it takes every line and gives it down to a single point at the origin. That's okay. But now when you try to inverse this, the only place that really matters is 0, and you don't know what vector you started with. You could have started with, the red one, the green one, or this one, or some other one. You don't know where you started. So this is also not going to be invertible. This also has to answer the question, which one? All right, with that, your assignment this time is just to kind of do a lot of this. Figure out what the transformation is, figure out what the inverse is, describe it geometrically, and just find the inverse matrix. To find the inverse matrix, you have to use this idea of using the basis vectors to come up with that matrix, just like we did here. And you have to do the same thing with the inverse. Just a lot of practicing. One of the main takeaways of this is just to understand exactly what the inverse transformation is doing. It's undoing a transformation, and also experiencing that not every linear transformation has an inverse, right? So with that, I'll leave you to that, and I'll see you next time.